transit. Okay. And then because you make use of radio waves as well, right?
Yes.
And these waves are focused on the ions or the electrons?
The radio waves are focused on the ions. I don't know how far you read. In the plasma, you have a strong magnetic field of a few Tesla, and ions and electrons gyrate around the field lines. And the gyration frequency of the ions is much lower since they are more heavy. So these typical gyration frequency, which are also the frequency where we heat the ions, are 30, 50 megahertz, something like that.
Okay.
So that's radio frequency.
Okay.
When we heat the electrons, we have to go to much higher frequencies since their mass is small, and then we are in the 100 gigahertz range.
Okay.
So it's basically the mass ratio.
Okay. And those are the
gigahertz is technologically more demanding. So in fusion history, people started to heat the ions because radio waves were easy, but microwaves have some advantages. So in principle, they are more expensive. So if the money comes into play, maybe the radio frequency is still in. But the microwaves have the advantage that you can emit them optically. They travel like light. Okay. So you just need a mirror and you send it to the plasma and it will be absorbed.
Okay, but so you say that with microwaves it's more complicated, they're more expensive?
At the moment, because it's a technology which is mainly driven by fusion, to so-called gyrotrons, these are tubes which produce this microwave, and you need megawatts, so one tube has a megawatt. And this is at the moment quite expensive to buy, while you can easily buy a radio frequency generator of a megawatt. There's now solid state technology. So in principle, building up a radio wave system is cheaper than building up a microwave system.
Okay.
And at the end, when we have a reactor, if both of the systems work, for the microwaves, for the radio waves, you need a sort of antenna in the tokamak, which is a bit more complicated. Emitting or heating the plasma with microwaves is much easier. But at the end, maybe we want to have both also in the reactor, because these the electron cyclotron heating, which heats the electron, only heats electrons. And the radio waves also heats ions and electrons. And for some reasons, you may want to have a wanted ratio of electron to ion heating in a reactor to optimize the plasma performance.
Okay.
Therefore, we keep both at the moment.
Okay.
We continue with both heating systems.
All right. And then you support the heating with deuterium beams.
This is the workhorse at the moment. So, for example, at Asterix Output, we have 20 megawatt of heating with deuterium beams, 5 megawatt of heating with the electron cyclotron, the electron range, and about 6 megawatt for the ions with the radio frequency.
Okay.
So you see the 20 to 6 to 5, that's the workhorse, the beams. Right. But this may be different in a reactor because increasing the size, scaling it up to reactor size is in principle easier for these wave heating systems. Because for the beams you have to go to higher voltages for the acceleration, and this is more complicated. Because you have to deal with one MeV, which you have to isolate in the radioactive environment and so on. So technologically, maybe it may shift that wave heating will be more important in a reactor, but all three systems may be there.
Okay.
But there's a preference for the wave heating.
Okay.
If it's possible.
That's very interesting. Let's see. And the other question we had was for the diverter, because we read that, right, the only heat transport is or the appliance of the diverter is to transport the heat and to manage the contamination with, or the what's it called? You have the tungsten particles. Hoe heet het, besmetting? There are some particles in the
tungsten produced in a diverter, and this needs to be optimized. That means brought to a very low value.
Okay.
So the task of the diverter is basically you have to exhaust the power. Most of the power which goes into a tokamak has to be exhausted, and in present machines this is mainly done in a diverter. In a reactor also we you will use radiation also in the core plasma and distribute the radiation about the much higher surface area of the whole vacuum vessel there. But this is quite simple and straightforward. And the diverter is still, it can digest about 15 megawatt per meter length in the circumference. This is at the moment the limit we think we can achieve. And the diverter needs to optimize the plasma conditions in front of the target. That you still get rid of the power, so the power has to be transmitted from the plasma to the material, which is tungsten, and from the material then to the cooling pipes, which can happen only in a certain temperature range.
Okay.
And we use tungsten because it can become very hot.
Okay.
That's the basic advantage. But we still have to provide conditions that not too much tungsten is eroded. As of course, one thing we have to avoid that tungsten shows up in the main plasma. If there's too much tungsten in the plasma, we have too much radiation, and the fusion reaction will stop because the plasma will be cooled by the radiation. So we have to avoid that too much tungsten gets into the plasma. That's about a concentration of a few 10 to the minus 5 of the electron density, so it's quite low. But the other point is we have to avoid tungsten sputtering because such a diverter should last for 2 years at least. And if you have too much sputtering, you would erode away the surface, and then you would erode until you come to the water pipe, and then the diverter would be destroyed. This has to be avoided.
Yeah.
And you can switch off erosion of tungsten more or less completely when you have a very low plasma temperature in front of the surface. So that's the operational point of the diverter, that in terms of, so we have to operate the plasma in front of the target at about 3 electron volts, which is 30,000 Kelvin. And when we manage to do that, then the tungsten sputtering is almost zero. And then the diverter will have a long lifetime and everything is fine.
Okay.
When it gets hot, we run into problems.
All right. And you you upgraded the diverter a few years ago, right? With from a tungsten coating to tungsten tiles.
Yes, just the outer just a part of the most challenged part of the diverter. We have massive tungsten tiles now. Yes, this was done 3 years ago.
Okay.
Before we had tungsten coatings on carbon, which is good, but when you have some erosion, the tungsten is gone after a while, and also there may be problems with delamination, that the coatings are released from the carbon when it gets too hot.
Okay.
Therefore, and it's also more relevant. We want also to do relevant things. We want to operate Aztec's upgrade in a mode and by systems and means which are as close as possible to a future reactor. That means we go to materials we foresee for a reactor. We also go to magnetic steel now as a plasma-facing material in the core, in this main chamber. And so we try always to get Aztec's upgrade as close as possible to what we think will be the situation in the reactor.
Okay, and for the reactor then, of course, we need a source of tritium, right?
Yes.
So
that's one of the major technological tasks. The tritium has to be produced in the reactor, and we have to produce exactly 1 tritium atom for 1 tritium we use up. This is also important because people are concerned about proliferation, and fusion reactors are spread around the world. People could use them to produce tritium, to use it for hydrogen bombs or whatever. But in fact, it's even quite a challenge to produce to produce 1 tritium per 1 tritium used up. So when you do nothing, you will get 0.9 or something like that. So it's technologically a challenge really to produce the tritium you need. Because it's clear when you have several fusion reactors at the world, you cannot buy tritium, and it's very expensive to produce it with other means. So you have to produce it in the fusion reactor, in the so-called blanket.
Okay, and that's the lithium blanket.
That's a lithium blanket, and the challenge is, it's just given by the atomic reactions. The blanket has to circumvent almost all the plasma. There are not too many holes allowed in the blanket. That's also an issue for the neutral beam heating in the reactor because it needs quite a big hole to go through. The more holes you have, you get in danger that you come below this breeding ratio of 1. So a few holes are allowed because there are two different lithium isotopes. One of them uses up the neutron and produces a tritium, but there's another reaction where you get the neutron back and you can get another try. So you get a tritium, get the neutron back, and but by this you can compensate a few losses of neutrons you have. But generally, when you design a fusion reactor, there are no strong losses of neutrons allowed. So there are no big holes allowed in a blanket, and also no structures between plasma and blanket where the neutrons are absorbed and do some, for example, transmutation. When you have a transmutation reaction in steel or whatever, then it's forbidden. So this also means that copper will probably not be used in a fusion reactor because it's a loss of neutrons, and this can't be accepted.
Okay. So you at the SX upgrade, you also make use of this lithium blanket.
No, in present, no present tokamak has a blanket.
Okay.
We all use just deuterium. That means we don't have fusion reactions. There were only a few experiments with true fusion reactions in TFTR. That's an old tokamak in Princeton in the USA. But the major experiments were done at JET. That's the Joint European Tokamak in Akallen. They had a few weeks of operation with tritium, just to show that the reactions in the plasma are so the tritium-deuterium fusion reaction, that it happens as what you predict, that the cross sections are okay and so on. But JET has no blanket, so there was no breedium. So they bought the tritium from Canadian fission reactors. You can buy a few 100 grams of tritium, but nothing which would be needed to operate a fusion reactor for a year.
Okay.
And there will be another tritium experiment in a few years in JET as well. They started purchasing the tritium again. You have to buy it over several years because there's no big market for this in the world. But there's no blanket at the moment. This will be tested later in the big worldwide project, the ITER project in Cadarache. ITER is a bit delayed, unfortunately, so it will start, I guess, around 2025. There is no official number at the moment. They tried to make a new official timeline, but it was they were asked to even accelerate it a bit, so they have to work on that. But it will be around 2025, and it will take 8 years or so until they use DT and they really produce massive fusion reaction in several megawatts. But then in a later stage in ITER, blanket modules will be tested just to test the technology of the tritium breeding. There are different technologies at the moment which are discussed. All of them have advantages and disadvantages. You can use water, or you can also use helium as cooling. You can use liquid lithium metal, or you can use solid lithium. And this will be tested. There will probably different blanket types be installed in ITER. And then after that, we will know what is the best way to breed the tritium. That's one of the major challenges, of the 2 or 3 major challenges fusion had, that you really breed the tritium.
Yeah.
Deuterium is trivial. You just get it out of water, and that's therefore we call fusion sustainable, because the amounts of deuterium and lithium in the world are infinite in principle.
Yeah.
So from that point of view, it's sustainable. But you have to go through the step to breed the tritium out of the lithium.
Okay.
That must be a clear component of a tokamak or of a fusion reactor, which can also be a stellarator.
Yeah, because of course without the tritium, the tokamak won't produce any energy.
Yes. The advantage, of course, is that you use up the tritium as you produce it. That means you have no transport of this. Tritium is not very dangerous. It's radioactive, but it's a very low energy beta radiator. But you do not pile up a big inventory, and that's one major part of the inherent safety of the fusion. That you have only fuel for a few minutes in the plasma. That means the energy density which would be available for an unwanted reaction is very low, because you have just a low amount of fuel around. While in a fission reactor, as you know, you have the fuel for several years of operations and that's in principle the danger, the stored energy which is there, and this is not the case for fusion. Therefore, a fusion reactor will never be able to explode because it's just a few seconds of runtime, which you can compile up in energy.
And is that the runtime? Is that something that you want to improve or extend? Would it be better to have a longer runtime for the fusion reactor to produce more energy, or do you want to have a lower or a smaller runtime?
Of course, the runtime. What do you mean with runtime? A fusion reactor hopefully will run for 20, 30 years when you build because it's expensive, but you probably will have to do maintenance. For example, it may be that you have to exchange the diverter each 3 years. And of course, in view of economics, when you have some intervals for maintenance, you want to have these intervals very short maintenance time and long intervals in between. But this is at the end when first of all we have to prove that fusion runs, that it works, and probably the first prototype reactor will have not very long run times because you will learn a lot how to can improve the design. But when you think of a large series, really workhorse fusion reactor, it should have long run times and very short maintenance intervals. Otherwise, it would not be competitive. At the end, it has to compete with renewables with the price of cost of electricity at the end, which should include everything. For fusion, the fuel doesn't cost anything, but of course, it's very expensive to build up a fusion reactor. So you have the capital investment, basically, which you have to earn, and which will dominate the cost of electricity you get at the end. And of course, the longer it runs, the cheaper the electricity gets.
Yeah.
And this will be then a later optimization criterion once you have mastered the technical challenges. Because at the end, if it's much more expensive than solar or everything or wind energy, then it will not be used. And so it must be competitive, and it will probably be a ground, so a quite constant power flux. The renewables have the problems that solar energy, wind energy, everything is very fluctuating, and a fusion power reactor will be a base plant, for example, of the base electricity supply, exactly, which has to be there all the time.
As the X upgrade is as part of ITER, of a supporting role for ITER. Yes, right?
Yes, of course. ITER is, I think, all fusion experiments in the world try to cooperate with the ITER team to help ITER to get a fast start and to become a success. So we experts meet regularly with the ITER team that's divided into, of course, subgroups of research interests. So there's a lot of interaction of the worldwide fusion community with ITER. I think everybody, all countries involved in fusion, strongly collaborate with ITER, and there's also an exchange of personnel. So some good young scientists from here are now working for ITER. And I think that's very healthy because ITER needs experienced stuff, and you can only get experience in a present device, and then you can nicely prepare the operation of ITER, which will still need some time. So I think that's a very good collaboration with ITER.
And do you think the ASX upgrade will still be relevant in a couple of years, or do you think ITER will be,
well, if it's still
of course, yes. I think our plans at the moment. In the past, we worked, of course, a lot for ITER, and the knowledge went into this ITER. There are books, the ITER physics base, for example, where we contributed. And now, of course, we still try to optimize the plasma scenarios which ITER will use. There have been scenarios foreseen, but we found that some of them may be changed a bit to different directions, and this is what we are working on partly here. And on the other hand, we work also for a demo, so our work shifts a bit for developments required for the successor of ITER, which will be a demonstration reactor. And one point, for example, which we will investigate in the future. And I think Aztec's upgrade at the moment, our plans foresee 10 years of operation. At least so we have very clear plans for the next 5 years. We have also investments we have to put into the German system. We have to ask for it well in advance, and also the European system. So we have clear projects which will finish in 2019, which extend our machine, which bring us even more power. And then we just launch other ideas for a new proposal we will send this year, and this will then bring our operation up to 2024 or something like that, or up to the ITER start more or less. And this will partly be devoted to developments required for a future demo. And there's one, we are world-leading machine regarding the diverter concept here regarding power exhaust. That's one of our major thrusts. Our machine has been optimized for that. Other tokamaks have different things where they are good, but we are really the world leader for the power exhaust. And we have this standard diverter concept where we have shape of the diverter, certain plasma conditions, and then probably in 5 years from now we will also try to investigate alternative concepts at very high power levels. This is at the moment just directed to a demo. So ITER will have a diverter very similar to the diverter in Aztec's upgrade now, and this will not be changed in ITER, so ITER design is fixed. But a future demo may have a slightly different diverter, and there are also in other machines investigations of these concepts having started, but they cannot operate at very high heating powers, and that's a major assess we have here, that Aztec's upgrade can have very high heating power and really challenge the diverter. And this will be then our task maybe 5 years from now to test this with alternative diverter geometries.
Okay. So how many different concepts do you have for that? For the diverters?
Sorry, the sound was just bad. Please, can you repeat?
Okay. So you say that in the coming 5 years you want to experiment with some other concept of diverters. In what way do they differ from each other?
Maybe you looked at so it's just the magnetic geometry. Maybe you have looked at so in the standard diverter you have coils which are far away from the plasma, which produce a null of the colloidal field at the so-called X point. That leads that the magnetic field lines are bent around and then led into this diverter chamber. And there you have a certain impact angle of about 2 to 3 degrees of the field lines on the surface. This you need to protect the surface from overheating, and you also have to sustain a certain plasma state, which we call detached state, which allows to produce these low temperatures which are required to avoid tungsten sputtering. So that's a quite simple magnetic geometries, but there are theories or theoretical calculations, also some experiments in smaller devices that you can make more complicated magnetic geometries, which, for example, allow you to get to spread the plasma magnetically about larger surface areas. Just by, for example, not make the magnetic field null, but also make the derivative of the magnetic field null. That means just more or less more distributed power flux, or you divide the power flux in the diverter by adding a second X point, so to say, to divide it by 2 and redirect it into 2 directions. So there are magnetic possibilities to further improve the diverter operation, which may work or may not work. We don't. Maybe it will work, but the question will be: is it necessary? Because it will add additional cost, and that's sort of risk mitigation for the case that the standard diverter in a demo device will not work. I think the standard diverter will work, okay, but with such a costly project. You cannot just say it will work, and if it doesn't work, we fail. This is not acceptable. So this is called risk mitigation. So if the standard diverter fails, we will end up with another diverter concept, which is, for example, snowflake diverter. It's called because the magnetic geometry looks like a snowflake. Then you need additional coils. You lose some plasma volume, so it makes the electricity at the end a bit more expensive. But this is better than a complete failure of the project. So that's risk mitigation, and we hope that we can live with the standard one, but we have to prove it. And this will be then our task, or what we partly do then 5 years from now or so. Maybe until ITER starts. And when ITER starts, we have to see.
Okay. And what are
maybe
your...
Aztec's upgrade then fails at some point. Aztec's upgrade operates now for 25 years. And of course, at some point, and we have, it was not designed to live forever, of course. That's also for other tokamaks. And at some point, when you lose a major component, at some point you may decide to stop. For example, if a toroidal field coil would fail in Aztec's upgrade, which this would bring us down for several years and cost a lot of money. Because you have to dismount everything to come to the point. We have one reserve coil around, but it would cost a lot of time and money to bring it in.
Exactly.
But fortunately, normally this shouldn't happen. So, but then after such a long time, something may fail.
Of course. And how do you see the future then? Are you quite or skeptic about the fusion power part, in which you think that it may not be economical relevant in the future for example, demo project? Or would you think that it, or in your opinion, would it be more likely that it would be economical, very important, and could compete with, for example, solar power and wind energy?
I think nobody knows. If people say they know what cost of electricity of a fusion power plant is, I think you cannot take this serious. There are so many points in the development, and of course the first thing will be expensive. This is clear, and the question is by how far can we reduce the cost? You just have the cost of investment. That's the advantage. Once you have built the thing, it starts earning money, but it needs to run a long time. And investment, ITER will cost 12 billion or something like that, and a demo reactor will cost 20 billion. And you need to produce a lot amount of electricity to earn this money back. But maybe after some time you learn to build it cheaper. Normally this happens for all big technologies, that they got cheaper. Like for the solar cells, they also took some time to get down. So I cannot tell. I think from when you make forecasts at the moment, it may be that it will be very feasible and very cheap. Not very cheap. This is clear. It will not be far beyond 10 cent per kilowatt hour, I would guess. But you really have to ask: is it competitive with wind and solar and other things? Maybe biogas, biofuels you have to avoid because it competes with food production at the end. So all these things. So maybe the price of electricity will go up, and it's clear that it has to be competitive, and I would hope it's competitive, but I cannot tell you. Maybe it's 50-50. But I think our idea is that mankind should not take the risk to throw away this option now, because you even don't know what the cost of electricity for the renewables is when you think about the world population. And I think in Europe you can more or less see what comes, but what is about China and India and so on? If they start to produce as lot of energy per head as we do, then it will be quite complicated. So I think all the projections for the future are uncertain, as is the cost of electricity. I personally be quite optimistic for the fusion. I have to be, of course. But if I wouldn't be, I would do something different. But I cannot tell you the cost of electricity, but I think it's an option. It's a risk mitigation for the whole mankind, I think. And therefore, I think we have to continue with fusion. In Germany, it's not so easy, as you know, because fusion is in the same corner as fission, and fission has been more or less killed in Germany. So politically, it depends, of course, with which party is in the government. With this, Angela Merkel is a friend of us because she can think. She's a physicist. But if you would have a red-green a government of Social Democrats and Greens, I think we would face problems regarding our funding. And in Germany, it's even not easy now because we have the big coalition, so our funding is frozen. We cannot get more money. We just get next year the same as we get this year. Although other research areas increase with the natural increase rates, but we are frozen. Right. That's part of the compromise that we are allowed to continue.
Okay. And we had one question concerning a more technical part, because we read or we heard from the videos on the site that this tokamak increase in or the mass within the tokamak will increase with 120,000 tons during operation. Something like that we got from the video. Is that all from the plasma, or how should we see it?
The mass increases during... No, probably that's wrong. The mass doesn't increase.
No, like
so
that.
We have the weight of the coils, and then I don't know whether we read something about the stellarator. We have the stellarator. The tokamak has still the risk that it may be pulsed. So if it runs bad, a tokamak reactor may still be pulsed. That means... electricity production for several hours, and then you need half an hour break to recharge the magnets or the ohmic coils. We try to produce a tokamak which runs steady state, but this is also not clear whether this will be sufficient. Therefore, we have the stellarator concept, or we have just started with Wendelstein 7X in Greifswald, and the stellarator is inherently steady state, but maybe a bit more expensive than a tokamak. And maybe it's a bit more difficult to produce the plasma parameters. This we will learn in the next years. But there's also the risk mitigation for this failure of the tokamak concept. When the tokamak is pulsed, it's still no killer criterion, but it of course makes it more costly because you have to install an energy storage system on site because it will not be acceptable that you deliver electricity to the grid for 5 hours and then you just switch it off and do not deliver anything for half an hour and then restart again. So the grid has to be feeded with electricity all the time. That means you would need to have a heat storage probably unit, molten salts or something like that, which just increase the cost. I think these things become quite cheap because they are also used in solar heat power plants. So molten salt, which needs to be hot and then which is cooled down and delivers the electricity all the time. But of course, it's not a good concept to have a pulsed tokamak and a storage unit in between. But coming back to your question, so the plasma weighs nothing. So there's just a gram of plasma in the tokamak. It's a vacuum more or less, and you have the weight of the coils. And probably what you read was maybe the cold mass. Of course, a tokamak or also a stellarator needs to be superconducting. Otherwise, it would be too expensive to keep the magnetic fields, and you cannot cool it away. So the fields, the coils are all superconducting, and that means you have to cool down a big mass of 100,000 tons for a reactor to about 4 Kelvin or something like that. But this is no problem. Wendelstein 7X in Greifswald just started now, and it's a big machine and it's completely superconducting. Right. So this is now established technology, more or less.
Okay.
It's probably cold mass what you read, and that's really but most of the mass has to be cooled down because the weight sits in the coils, and the coils have to be cooled down because they are superconducting. Okay. You need liquid. At the moment, we need standard superconductors. People dream of high-temperature superconductors, which can be run with liquid nitrogen or so, but this technology is not established at the moment because a tokamak wants to have a very high magnetic field. The higher the magnetic field, the better. So around 10 Tesla. And I think this is not possible at the moment with the high-temperature superconductors. So we have to use standard superconductors, and they have to operate at liquid helium.
Okay.
What do you plan to do the coming 5 years? Wat ze komende jaren willen doen.
So after the because you mentioned what the plans were for the coming 5 years with these diverter concept, and afterwards, after these 5 years, what do you think will be the role of the STX upgrade? Will you still be involved in the?
So this new diverter concept we plan it at the moment. We have to get the money. We plan it so it will be installed at closer than 4 years from now. So that's really done for 5 years plus X. The next 5 years we have. There's also a European roadmap. I don't know whether you found that. The fusion in Europe is partly steered by the Eurofusion Consortium, which also sits here in Garching, but it's also in JET. And they have a roadmap for the development of fusion energy. And this roadmap at the moment tells that a demo power plant is ready by 2050. In fact, it will come a bit later because ITER has got some delays, and the 2050 would only be achievable if enough money is put into the system, and the money is not coming at the right rate at the moment. Maybe this changed, but so it will be 2055 or something like that. Maybe when this roadmap is done. Till then, in Astex upgrade, for example, at the moment we do extensions, we upgrade our heating systems, we increase the heating power we have for the electrons, this electron cyclotron heating. We install a new system which brings us 3 more megawatts of the heating system, and we are also upgrading our power supplies. It's when Astex upgrade runs, it consumes 200 megawatt for a short time. This power is provided by flywheel generators we have here on site. So we have big flywheels which are accelerated during minutes, and when we do an experiment, we slow them down within 20 seconds and produce a few hundred megawatt. You cannot just put the power into the coils. You need thyristors, so you need conversion units which convert the power coming out of the flywheels. You have to, of course, have a stable voltage and controlled currents and whatever. So it's a huge infrastructure you need to operate a tokamak. It's basically thyristor units. And we're upgrading these thyristor units to be able to increase our heating power to about 30 megawatt. The maximum we can do at the moment is 25. We have heating systems for about almost 30 megawatts installed, but we cannot use all of them simultaneously because we are limited by the power supplies. So in the next years, we increase our power supplies to reach the 30. And with this, we can really produce the power fluxes or the normalized power fluxes which are expected for ITER and a reactor. At the moment, we have 2/3 of the ITER value of the power flux we can produce. But with these extensions, we can produce hopefully the full power flux. And maybe it's just 1/3 of the way we have to go in the power exhaust, but maybe the last meters are the most challenging ones. We don't know at the moment. Therefore, we have to do it. We have to really show that we can handle the power as exactly the same normalized conditions as in ITER or in the reactor. And normalization is just circumference of the tokamak. So I think this is there's no cheating factors. We expect that then locally we have really the same conditions in the diverter, more or less as in a reactor. And then by these upgrades, which will be completed in 2019, I think we can do everything we need to do. And then the next step is then to try other diverter concepts. Exactly. And use also, of course, it's useful to have the high heating power. These concepts are being tested, for example, in England in a small device, but they don't have the heating power. And the Japanese and the Koreans also try to keep up with us. There's a competitor machine in China, but they cannot bring in the power we can do at the moment. So they can bring in 7 megawatts, and the machine has the same size as Astex upgrade. Okay. So they need a few more years to learn to handle these powers.
So that's why you went there, or is it all? Is it the fusion research very open source? Are you exchanging a lot, or
we publish everything open source, and in principle, since we all collaborate on ITER, there's a good collaboration. Of course, people have to keep in after ITER it may be more commercial thing. So I think ITER is set up in a way that all the countries get the basic technology to build it. But at the end, after ITER, we think for a demo it may be a more commercial part of interest, and then companies should go in and give money. And if then a company is able to produce components you need for a fusion reactor and sell them, then of course patents will start to be more important. But ITER is really public domain knowledge, so all countries can read the ITER design basis, all the facts and design criteria or the physics, everything is published. And we also collaborate quite well, even with the Chinese. Although we are aware that they are competitors, we have some collaborations with them, and it's sometimes also of use for us. For example, we wanted to have a new ICRF antenna for this ion heating, and it would have been quite expensive to build this antenna in Europe. So we had a collaboration with them. The antenna has been built in China. We got it for quite a low amount of money, and they learned how to build this antenna. So it was technology transfer, and we saved the money. And that's a very healthy collaboration. Okay. At some point, of course, we have to think of economic interests at the point, but I think at the moment, if we would start struggling about this, at the moment, it would not be very constructive. So everything should work together to get fusion running. And once I think ITER will define, the success of ITER will define probably the point where a commercial interest will come in, and then of course everybody will probably go its own path. But it's too expensive to develop things like ITER to really do it one after the other. Okay. The Chinese also dream of their own demo, and Europe has a demo in mind. Probably the Chinese will start first. At the moment they have money, but maybe the crisis will stop them down. But even we would collaborate on that, because at the moment collaboration is good for everybody. Okay. At least that's a general opinion.
Ah, that's great. Nog andere vragen? Okay. I think those were all our questions. So thank you very much for your time, and we will work this thing out and read some further into the literature. And I think you gave us a great base and really clarified some problems that we faced reading the literature so far. So thank you very much.
Okay, you're welcome. Thanks for your interest, and I can suggest look at the Eurofusion. It's called Eurofusion Consortium. They have lots of web pages where it's still under construction, because it has been started just 2 years ago. But I think find hopefully useful information, and also about the European plans, the European roadmap for fusion.
Okay. Thank you very much, sir.
Thank you.
Goodbye.
Bye.